Hello guys, welcome back to my channel. If you're new here on this channel, I'll be doing IGCSE physics content. So I'll be doing past papers, topic questions, and overall revision. So as we all know, 2023 is coming to an end. So to wrap up the year, today I'll be doing hardest questions of IGCSE physics in the year 2023. So I've gone through many of the past papers, all of the past papers in 2023, and I've chosen some of the hardest question and I'll be going through them, and I highly encourage you to watch till the end and try the questions by yourself, because it could really tell you where you're standing at. So let's start with the first question, or should I say this eighth question. So it says, state what is meant by a magnetic field. So a magnetic field is a region where magnetic pole experiences a force. So magnetic pole experiences a force. That's a definition of a magnetic field. Part 2. Define the direction of a magnetic field. So this is the direction of the force on the North Pole. On the North Pole. This is because we know that all magnetic fields are from the North Pole to the South Pole. Part B. Figure 8.1 shows a negatively charged metal sphere. On figure 8.1, draw 4 lines to show the electric field and its direction. So electric field is the direction in which positive, it's a diagram that shows the direction of positive charges. So we're asked to draw 4 lines, so we can draw 1. And then since this is a negative, that means positive charges would be attracted to it. So the direction is going to be towards the sphere. So we just draw 4 of them, and then we have to make sure they're equally spaced out. So this is our answer. Part C. Figure 8.2 shows a circuit. The 3 cells are identical and have 0 resistance. So these 3 cells have 0 resistance, and the resistors R1, R2, and R3 are identical. This is very important now. The reading on the voltmeter is 6 volts. When the diode is conducting, it has 0 resistance and 0 potential difference. So that means this diode won't be affecting the current in any way, except for the direction, of course. Determine the EMF of one cell. So we know that the voltage here is 6 volts, and we have 3 cells, 1, 2, and 3. So since all of them are identical, we can just do 6 divided by 3, which gives us 2 volts. So our answer is going to be 2 volts. Part 2. Determine the ratio of the PD across R2 to the ratio of the potential difference across R3. So let's look at the diagram. So the current flow is going to be flowing like this. Up until this point is going to be 6 volts. And now over here it's going to be split in 2 parts. So since these 2 resistors are identical, it's going to be 3 volts over here and 3 volts over here. Now this continues, and then these 2 pathways meet again over here. So now the 3 volts add up, and then over here it becomes 6 volts again. So R3 is receiving 6 volts, R1 and R2 are receiving 3 volts. So the ratio of R2 to R3 is going to be 3 to 6, which can be simplified to 1 to 2. So this is our final answer. All cells are reversed. So when the cells are reversed, the flow of current is also going to be reversed. State and explain the change in current in R1. So this is R1. Let me just erase everything so I can make it clearer. So now the flow of current is going to be clockwise. So it keeps on moving here, and over here we have the diode. Now this diode only allows current in one direction, so it's not going to allow current in this direction, so no voltage would be passing through to R1, so we just be moving this side. So that means the current in R1 is going to be 0, and this is because the diode is in a different direction. So therefore it would not allow the current to flow through to R1. Determine the new value of the ratio of the PD across R2 and R3. So now this pathway is removed, so current will not be passing through this. So now let me use another color, and the flow of current is going to be like this. It's just going to skip the in-between line, and then this forms a series circuit. So that means 6 volts over here and also 6 volts over here, because in a series circuit the voltage does not change. So the value is going to be 1 to 1. Next question. Table 9.1 shows some properties and values of alpha particles, beta particles, and gamma radiations. Complete table 9.1. So we just have to fill out the table. But first, okay, so alpha particles, they have 2 protons and the number of neutrons. So alpha particles, they have 4 at mass number and 2 proton number. So this is the number of proton, and this is the sum of proton neutron. So that means we're going to have two neutrons and 2 protons. So the number of neutrons is 2. For beta particles, so beta particles are basically high-speed electrons. So they have 0 protons and 0 neutrons, and their charge is obviously going to be negative because they're high-speed electrons, and it's going to be 1.6 times 10 to the power of minus 19. Gamma rays. Gamma rays are radiation, they're not particles, so that means number of neutrons is 0 and charge is also 0, and they're stopped by, they have the highest penetration, so they are stopped by thick lead. That's 3 mark right there. Part B. Show how beta decay changes the nucleus of an atom. So during a beta decay, let's say we have a neutron, and this neutron is going to split into a proton and an electron. So how this brings a change in the nucleus is going to be, there's going to be 1 less neutron because the neutron has split into protons and electrons, and 1 more proton. That's our answer. Part C. A radiation detector used in a laboratory detects a background count rate of 30 counts per minute. A radioactive source is placed in front of the radiation detector. The initial reading on the detector is 550 counts per minute. The half-life of the source is 25 minutes. Calculate the expected reading on the detector after 75 minutes. So we know that the reading is 550, but the background radiation is 30, so we just subtract 30, which would give us 520. So the half-life is 25 minutes, so every 25 minutes the count rate is going to half. So the first 25 minutes is going to be 520 over 2, which is 260. The second 25 minutes, or after 50 minutes, we also divide by 2, which gives us 130. And finally, the third 25 minutes, or after 75 minutes, we also divide by 2, which would give us 65. So after 75 minutes, it's going to be 65, the count rate, 65 counts per minute. Now we're asked the expected reading on the detector. So we also have to account for the background radiation. So that means it's going to be 65 plus the background radiation, which is 30, and our final answer is going to be 95 counts per minute. State 2 safety precautions taken when moving, using, or storing radioactive sources in a laboratory. So the first one is limit time of exposure. And the second one is going to be they should be stored in lead boxes, because that means radiations will not be able to escape. So store in lead boxes. Next question. A student investigates the efficiency of a filament lamp. Figure 4.1 shows the filament lamp with its glass bulb immersed in water in a beaker. The reading on the thermometer is the water is 19 degrees Celsius. Only the glass of the lamp is in contact with the water, and the electrical connections are completely insulated. So there's no wastage of energy, or there's no heat coming out. The lamp is switched on. At the end of the experiment, the temperature of the water is 21.5 degrees Celsius. The mass of the water in the beaker is 600 grams, and the specific heat capacity of water is 4,200 joule per kilogram degree Celsius. State that the increase in the internal energy show that the increase in the internal energy of the water is 6,300 joules. So the formula is Q, which is the energy, is equals to the mass times specific heat capacity times the change in temperature. So the mass is 600 grams, but we have to convert it into kilograms, so it's going to be 0.6 kilograms times the specific heat capacity is 4,200 times the change in temperature. So the initial temperature was 19 degrees Celsius, the final was 21.5. So we do 21.5 minus 19. Now that would be equal to 2.5. Now we can multiply all these to find the energy. So 0.6 times 4,200 times 2.5, which would give 6,300. So this is equal to this one. So we have proved it. Next question. In the experiment, the lamp switched on for 500 seconds. The power supplied to the filament lamp is 13 watts. The useful energy from the lamp is transferred as light. The energy that increased the temperature of the water is wasted energy. Determine the maximum possible efficiency of the lamp. So if the total power supplied was 13 watts and it was switched on for 500 seconds, we can calculate the energy. So we know that power is equals to energy over time. If we rearrange this formula, energy would be power times time. So the energy would be 13 times 500, which would give 6,500. So this was the total amount of energy supplied, and the energy wasted was 6,300. So if we subtract 6,300 from this, we would get the useful energy, which is 200. So 200 watts, 200 joules is the total amount of energy used to light the lamp, the useful energy. So efficiency is the useful energy, 200, over the total energy, which is 6,500. Then times 100. Now this would give us 3.1%. So maximum possible efficiency is 3.1%. So the lamp is not pretty efficient. The efficiency of the lamp is less than the value determined on the previous question, so it's less than 3.1. So just one reason for this. So one of the explanation could be that the temperature could be the thermal energy could be transferred from the water to the beaker and then to the bench the beaker is standing on, so it's unpredictable. So we can write the thermal energy is transferred to the beaker and then to the bench. That's our answer. There could also be other multiple explanations for this. Number 5. Figure 5.1 shows a block ABCD made from glass, and that has a refractive index of 1.5. The block has one curved side AB, so this is the curved side AB, and three straight lines BC, CD, and DA. So this is a diagram. There are right angles at C and D. The curved side AB is 1/4 of the circumference of a circle that has its center at point P. So this is point P, and then this quarter circle is 1/4 of a full circle with a center of P. So this quarter circle is part of a circle with a center P. A ray of monochromatic light enters the block through the curved side AB and strikes side BC at P. So it strikes side BC at P, right at the center. Some light emerges into the air and some light is reflected. State what's meant by monochromatic. So monochromatic is a type of light that only has a single wavelength. So light that has single wavelength. So due to the single wavelengths, it would have a single color. B. Explain why the ray of light does not change direction when it enters the block through the side AB, so through the curved side. So one of the reasons for that could be that the line is moving along the normal line. So it's moving along the normal. So there would not be any refraction of light. So there's no refraction of light. That's the answer. So that the critical angle C for the glass on refractive index 1.5 is 42. So the formula for refractive index with critical angle is 1 over sine C. So we have the refractive index, which is 1.5, is equals to 1 over sine C. So we can do cross multiplication. So 1.5 times sine C is equals to 1. So we can divide both sides by 1.5 to isolate sine C. So 1 over 1.5, that would be 0.666. And then we can do shift sign on our calculator to find that, and then it would be 41.8, which is approximately equal to 42 degrees. So that's how we find the critical angle. D. Figure 5.1 shows that the angle between the ray of light and line AP is theta, where the line AP is at right angles to side BC. Angle theta increases to 45 degrees. State and explain what happens to the light that strikes P. So if angle theta increases to 45 degrees, that means it has exceeded the refractive index, which was 42 degrees. So the explanation could be, so if the incident ray surpasses the critical angle, that means there would be total internal reflection. Be a total internal reflection. That is because the angle of incident, so I, was greater than the critical angle. That's our answer. When theta equals 45 degrees, the reflected light hits side CD. Describe what happens when this reflected light strikes side CD. So let's go back to the diagram. So we can see that this light, the reflected light, hits side CD. So if it's hit side CD, this is going to act like a mirror, and it's going to be reflected. So all the light is going to be reflected back. So we can write all the light is reflected. All the light is reflected. Let's move on to the next question. Question number 9. Figure 9.1 shows the Sun as the central dot and the planet Saturn, Jupiter, Earth labeled. So we have Saturn, Jupiter, and Earth labeled SO, JO, and EO. The planets orbit the Sun anticlockwise. From the Earth's orbit, the planets appear aligned. Assume that Saturn takes 30 years to orbit the Sun and that Jupiter takes 12 years to orbit the Sun. On figure 9.1, mark the positions of Saturn and Jupiter 5 years after the original positions shown. Label these positions S1 and J1. Show you're working. Okay. So this question is a bit tricky. So this is the Saturn, and then it takes 30 years to complete a whole circle. So we know that it goes anti-clockwise. So it takes 30 years to do a complete 360 degrees or a full circle. So 360 degrees. And we ask the position of Jupiter and Saturn and Jupiter after 5 years. So after 5 years, it would become X. So it would be 360 times 5 over 30. So that would be 360 times 5 over 30. That would give us 60 degrees. So Saturn is going to be 60 degrees from the original position. So S1 is going to be 60 degrees. So I don't have a protractor, but then this angle over here, it should be 360. I mean, it should be 60 degrees measured. So, and we have our point S1. And for Jupiter too, we do the same. Let me use another color for Jupiter. So we know that Jupiter takes 12 years. So in 12 years, it does 360 degrees, a whole circle. So that means in 5 years, it would do x. So it would be 5 times 360 over 12. So 5 times 360 over 12, that would become 150 degrees. So it would do a complete 150 degrees. So it would be somewhere around here. So this angle should be 150 degrees. And then Jupiter is going to be somewhere here. We can label this as J1. So we just have to make sure this is 150 degrees. And then for the Saturn, it's going to be 60 degrees. So for our working, we can just put this part over here. We can just put this part. Let's move on. Question B. On figure 9.1, mark the positions of Saturn and Jupiter 20 years after the original positions shown in figure 9.1. Label these positions S2 and J2. For this question, we also do the same thing we did for the previous one. So we know that Saturn takes 30 years to do a 360 degree. So after 20 years, it would become X. So it would be 360 times 20 over 30. So that would give us 240 degrees. So 240 degrees. So the new position of S2 is going to be somewhere from the center over here. So that means this whole angle over here is going to be 240 degrees. That's for S2. And then for Jupiter, we know that Jupiter takes 12 years to do 360 degrees. And then in 20 years, it would do X. So we do crisscross, and then X would be 600 degrees. So obviously this is a circle and the maximum one is 360. So we know that it does more than one revolution. So we do 600 minus 360 degrees, which becomes 240 degrees. So this is also going to be at 240 degrees. So it's going to be in the same alignment as S2. So we write J2 over here. So same alignment, which is also 240 degrees. 2. State what is observed from the Earth's orbit after 20 years. So when we go back to the diagram, we can see that after 20 years, J2 and S2 are going to be aligned. So we can just write that. So Saturn and Jupiter are aligned. So Saturn and Jupiter are aligned. C. I choose two words from the list to describe each planet. So Jupiter is going to be gaseous and large. So large and gaseous. And Earth is going to be the opposite, rocky and small. Small and rocky. Part 2. The average density of Jupiter is much less than that of Earth. The gravitational field strength at the surface of Jupiter is greater than at the surface of the Earth. Explain how these differences in density and gravitational field strength are consistent with your answers to CI. So for density, Jupiter has lower density because its made of gas, and gas has less density than rocks or Earth, which is rocky. So has lower density because it's made of gas. And when you talk about gravitational field strength, Jupiter's is larger because Jupiter is bigger and it has higher gravitational field strength, and because it has more mass. It has more mass and it's larger. That's gonna be our answer. Part D. The average density of Jupiter is 1,300 kilograms per meter cubed. The volume is 1.4 times 10 to the power 15 kilometers cubed. Calculate the mass of Jupiter. So we know that density equals mass over volume. So mass is going to be density times volume. So density is 1,300 and volume is going to be 1.4 times 10 to the power of 15. So now when we multiply this, we can put it in standard form, and then we can get 1.8 times 10 to the power of 27. That's going to be our answer. Kilograms, of course. So we can see that Jupiter has a high mass, very high mass. Number 10a, I believe this is the last question. Show that 1 light year equals 9.5 times 10 to the power of 15 meter. So we know that light year is the distance light travels in 1 year. So we have the speed formula, which is speed equals distance over time. We can rearrange this, and distance becomes speed times time. So speed of light, we know it's going to be 3 times 10 to the power of 8 meters per second. But for the time, it's going to be 1 year. But we have to convert this into second. So 1 year is the same as 365 days. So 1 year is the same as 365 days. And 365 days, in each day we have 24 hours. So 24 times 365, we have 8,760 hours in 365 days. And we know that for every hour, there's 3,600. So 1 hour is 3,600 seconds. So we multiply this by 3,600. So we would get like 31,500,000. So 31,536,000. So now we have this. So now we multiply 3 times 10 to the power of 8 times 31,536,000. So when we multiply this, we get 9.5 times 10 to the power of 15. So we have proved it. BI. State one measurement that is taken when determining the speed v at which a galaxy is moving away from the Earth. So that is going to be redshift, because redshift is what we use to determine the speed of a galaxy moving away from the Earth. Write down the equation relating v and distance of a far galaxy. So whenever we're talking about the distance of a galaxy and the speed of a galaxy, we're talking about Hubble's constant. So Hubble's constant is going to be the speed over the distance. State how the distance of d of a far galaxy can be determined other than by using the equation in 2. So how we determine the distance of a galaxy is by the brightness of a supernova. A supernova. Supernova is one part of the life cycle of a red supergiant star. So it's around the end. So a supernova, it's what forms after a red giant has decayed. So the V in Hubble's equation is determined by redshift, and the distance is going to be by the brightness of a supernova. So if the supernova is far away, the brightness is going to be decreasing. If the supernova is closer, that means brightness would increase too. So that was the last question. If you enjoyed, make sure to like and subscribe. Or if you have any comments, questions, or suggestions, make sure to drop them down below in the comments. And thank you for watching.